It's my great pleasure to introduce Mary Hayhoe. Mary Hayhoe is a professor in the Center for Perceptual Systems at the University of Texas, Austin. Mary's research is in developing virtual environments and experimental paradigms for the investigation of natural visually guided behavior. And this is a fascinating area to me because I'm personally involved in research which approaches vision from the other end, which talks about like, how can we build up algorithms? And Mary's been working on like, let's understand humans who know how to do this and understand how they do this. So Mary has served on the board of directors of Vision Sciences Society from 2011 to 2016 and was president in 2015 and was awarded the David R. Teller Award in 2017 for her contributions to vision research. So I'm excited to hear about what insights Mary can shed and what we can learn from this for robots. So with that, I hand over to her.
Thank you. Okay. Well, I'd like to echo the sentiment that it's really great to actually see real people again. So this is my first outing, and let me get rid of this. Okay. So I'm going to talk about something completely different, which is human behavior, but with a bit of a difference. So most of the work, sadly, in understanding human vision is lots of great work, but it's the structure of the experiments just don't tell you very much about how vision actually allows you to get around the world. And so you have a series of trials. You're asking one question, like, can you detect this motion signal? What's your stereo vision like? And the experimenter is telling you what to do. But in ordinary behavior, it's evolving in time. You're making the decisions about what to do. You're actively selecting information from the environment, and nobody's telling you what that information should be or what you need. And so one of the things I like about this is that this is, we want to know, okay, how do you build a human to do these things? And so this is very similar to the problem in robotics. How do you build a robot to do these things? So first of all, we just need to know what people do. And this is John Mathis walking across the road, and he's wearing an eye tracker. There's a camera on the head. That little blue cross is where he's looking. And so you can see your eyes are very busy. And we're not really aware that we're so actively getting different kinds of information. And so here it's slow-mo, and you see he looks at the curb. He looks at the girls because he wants to walk around them. He wants looking where he's going, the pedestrians, et cetera, et cetera. So the way you can think of that, this is, you've got this sequence of decisions. And so what's controlling where I go now? So you look at the right place. So how did you see the curve? You managed to look at the curve. You look at the pedestrians who might bump into you. And so we're making the right decisions at the right time. And how is all this working? Just before I go on, I'd just like to share some terminology. So these very rapid eye movements are saccadic eye movements, are high velocity movements. You're not getting any information because of image blur. Then the information you're collecting is during these periods we call fixations, which are a couple hundred milliseconds. And so that's when vision is happening, but then you're going on to the next thing. All right, and so to understand vision in the context of action, we need to know what information is needed for behavior, different kinds of behavior, and how is this information used to make a decision of where to walk or where to look. Now, this is just to say that in the last, 15, 20 years or so, people in human motor control have adopted this conceptualization of the problem of using statistical decision theory. It's just a convenient framework, even if it's not complete. But the idea being, of course, you want to evaluate the world state in order to make a decision. In order to do that, you need to get sensory data, and then you've also got your priors about what's out there in the world. And you need to take into account the costs and benefits of that action. And so I'm going to be talking about 3 of these things, in particular, the collecting the sensory data, the importance of memory, and also perhaps most important is the cost function, how this is sculpting every tiny little decision you make when you're crossing the road. All right, and so I just want to make sort of back into a little bit about the brain and how this makes the cost functions incredibly important to think about. And so what you have here is my cursor there. Okay, so here's the motor cortex and premotor cortex. And so you have this loop through the basal ganglia, this subcortical set of nuclei. And the basal ganglia is implicated in the choice of the action. And that happens because it's regulated by these dopaminergic reward circuits. And you also get this influence from this prefrontal cortex also on the motor cortical areas. And so every region in the circuits that control saccadic eye movements are influenced by these reward circuits. So it's a terrifically important modulator of the actions that we choose. So we did something just kind of simple. We measured walking outdoors. In ordinary terrains, we had a range of terrain difficulty. We instrumented the body with these IMUs. We have a binocular eye tracker, and you have to block the infrared, which is a bit of a pain. But eventually we got to do that. So first of all, what do we have here? On the right, you've got the view from the head-mounted camera. The black cross here shows you where you're looking. And so you're hopping along and very niftily getting information about where a good place to put your foot is. And you've got the eye and head signal down the bottom. And over on the left here, you've got the integrated eye signal and the body markers, and those little blue and red dots are where the feet will be going in the future. This little vector here is gaze on the ground. And we can, because we know where the eye is looking, we can align the images to the central fovea on the retina. And so we can actually use this to know actually what is the input to the visual system at this moment. All right, so that's nice. And so just a very crude overview of what's happening first and why these sort of various factors are involved that I was talking about. And so if you're walking along pavement, here, this is like the angle of gaze. So when you're walking on pavement, you're just looking in the distance where you're going. And so mostly you're looking pretty horizontal, but you only have to change the ground a little bit and make it just a dirt path. And suddenly you're spending a little more time looking at the ground. And then as the terrain gets more difficult, you're walking like this, right? Looking at the ground all the time. And so this is perfectly sensible, but in terms of understanding what's going on, you see the task goals are changing as the terrain gets more complex. This changes the gaze distribution, this changes the retinal input and the information that you're getting. So we need to know where you're looking. So again, just a little overview of this. If you're on a flat ground plane, you just need your prior. How do I walk? The ground is flat. You can just assume you don't need to bother programming individual steps. And your locomotion is controlled in these cases by low-level pattern generators in the spinal cord or brainstem. As the terrain gets more complex, now you've got to worry about getting that information. And so you're going to use gaze to get the sensory data, more complex sensory data. And so in this case now you need that cortical modulation of these low-level locomotor control systems. And Importantly, the cost function changes because if it's rocky, one is you need to find stable footholds, but it's also more difficult to work and it's costing you more energy. And people are really lazy. They always like the lowest energy solution. So, well, not always, but it seems to be a very important factor in even simple little situations like this. And so these decision circuits modulated by the dopaminergic reward machinery become quite important. And so this is just somebody walking in Shoal Creek. That was actually, you can see him, this was some of our early observations. And so he's actually wearing a welder's helmet to block out the infrared, which messes up the eye tracker. But however, so you can see, so what does he need to do? He wants to get to his goal, and you want to get there usually pretty quickly and as straight as you can. You've got to find foothold locations compatible with energetically conservative policies. You don't want to fall over, but you've got to do all of this and make these decisions within the time frame of a single step, which is about 400 milliseconds. And so once you start thinking about it, you think, wow, can we do that? And how does it all happen? We're completely unaware of it. So what do we know about locomotion? And a lot of the work historically has not even considered the visual system. It's on treadmills or flat surfaces. And so the bottom line is we don't know a whole lot about the visual motor control loop, these very complicated visual motor control loops. Now, previously, I showed you the integration of the eye and the body data, but that's not good enough if we want to know what we'd like to know is what is determining the choice of the path. And so to do that, you really need to have a representation of the terrain. And so what we do is use photogrammetry to recover the 3D structure using the sequence of head camera images. And this also allows us, because the IMUs are kind of drifty, by being able to link the terrain to the body, we can get much better estimates of where the feet are, and also we can get better estimates of where gaze is, because now we don't have these parallax errors. All right, and so this is what we get. This is our kind of data. Our little guy walking along, the pink spots are where his feet will go, and so these little blue cookie crumbs those are where his eye goes. And you see, we can analyze this data, and they actually look very, the gaze is distributed very pretty tightly around the actual foothold locations. But you can see also looking off, you have to make these decisions about changing direction. And so some of those fixations are distributed laterally as well. So what's going on? Can we actually predict where somebody would walk in a situation like this? And so first of all, we have to say, is there something to predict? We better be careful here. And so do people choose similar paths? And so here you've got two observers on the left there, and the blue is one person, the red is another person, and then they walk this route 3 times. And so you can see that in some cases, you can see, there we go. Up here, all trials and all observers are converging. This seems to be a good spot for walking. And you might do the same thing twice, but here different observers choose this path. There's something good about that. So a little more divergence over here. So there's clearly something to predict, although there's also a number of perfectly viable paths. All right. So what we want to know is, we want to know, why did you choose this path? And so what we did is we take a given footstep, and what's the path you took 5 steps ahead? And what are random paths? So we want to generate some random paths, but they have to be plausible. So if you're here, you're limited by your leg length, how far you can step, right? And so there's a distribution of step lengths, there's a distribution of changes in direction, and then also you can't step if so we generated a set of plausible random paths. And then what we did was we calculated for this 5-step sequence, you can calculate the how many changes in height there are, so that the mean changes ups and downs across there. And so that's what we got plotted here. These histograms are the sort of the mean slope. And so you can see the mean slopes, this pink, this disgusting pink plot here. Carl chose it for some reason. However, you clearly you choose the paths that involve less up and downs, and the random, the distribution of the random paths. So there's a fair bit of overlap. So again, suggesting that walk is a kind of, there's some flexibility. Some paths are perfectly fine and equivalent. So you're not really very tightly locked into a particular path. All right, so what is this? This is, what we did here was to look a little bit at the choice of more circuitous paths. And so for a 5-step sequence, you take, okay, the shortest, if I walk straight, what would be the height changes? And then if you choose not to do that, you want to measure how long the path is going to be that you chose instead. So you chose this instead of going straight. And so what we've got here, this is just one observer. So as the mean slope for a straight path increases, then you're more and more likely to choose a circuitous path. And so these don't show up very, the little blue spots, they're not too bad. So it's actually a pretty tight correlation. So it's kind of, again, neat that you're trading off the cost of these height changes with the cost of longer paths. And this was not a fluke for one subject. This actually happened for all 9 of the subjects. And and interestingly, I'm not showing you the data, but interestingly, this depends on your leg length. So people find nice operating points for their body. Again, it's kind of surprising that we're making these little trade-offs on this very short time scale. All right. So what we're talking about, so when you reconstruct the terrains, what we were using in the previous analyses was the actual mesh representation of the terrain, but we don't know for sure that this is what the subjects have access to. So what we took was the subject's perspective depth image, and we use this to train a CNN. So we got trained to recognize the real footholds, and so then we took another section of the path and tried to predict the footholds in that other section. And it doesn't do too badly. So the green circles are the actual footholds, and the heat maps are the sort of predicted footholds from the CNN. And so if you then say, how good is this? Then these are our 9 observers over here. This is this measure of area under the curve, the metric for area under the curve, to measure how good you're doing, well above chance, usually between 0.7 and 0.8, which is not too bad. And so this tells us that these depth features are actually important predictors of foothold selection. So we don't know if there are other things at this point, but this is about as far as we've got. So just to summarize, the factors that are influencing your path choice is you really like to avoid these big high changes. That's a little different from, there are other things that control your path, like a really big rock. You will avoid that, and often looks in the distance, you're probably seeing this is not a good way to go because it's a giant rock there. But on this sort of more local scale, you avoid these energetically costly ups and downs. Minimizing these high changes is also going to influence stability, and so it's a little bit hard for us to know at this point. We can't disentangle the stability constraint with the energetic cost constraint. And there's also flexibility in that. So, but the nice thing is that people are so neatly trading off the cost of these high changes with the cost of longer paths. And that's presumably one of the things that is guiding them when they change their, as you saw them weaving around a little bit, presumably this is what they're doing. The other point I'd kind of like to draw your attention to, and I didn't really show this very clearly in the talk, but the path choices that depend on the slopes over about 5 steps. So when you're walking, you're not just you're getting visual information. You're not just planning the next step. You're planning pretty much the next 5 steps. So the I don't know how we do that, but this seems, it would be nice to be able to model that. And so that simplistic diagram I showed you doesn't, I was sort of, again, I tried to just represent the fact that you've got 5 steps planned ahead, and you're also predicting what's going to be happening. And so to really have a better understanding of this, we need to understand this sort of kind of planning window of about 5 steps. I don't think it's much longer than 5 steps, because if you look at where the fixations are, they seem to peter out at about 5 steps. And then also that's at the point when you look into the far distance. All right. So these are the people involved in this. John Mathis, who started it all and is now at Northeastern University. Kate Barnon is at Indiana University. She was a graduate student here. Current graduate student Dan, and Carl Mueller has just left to look at satellite images and things like that. So thank you.
All right, questions? Luis?
I'm coming. Do you have studies on the kind of mean velocities?
Yeah. Yeah.
That would be also very interesting. And also,
yeah.
What information as well on age, person, and depending on the population you choose, right? But velocity probably is the key as well.
We haven't looked at the individual differences in speed, but yes, basically the first thing you do is slow down. And so, and that's where I think it would be nice to know if you actually kind of categorize the terrain and sort of general characteristics of the terrain to set some parameters like speed, gate speed. Yeah, that's I think that's how you preserve avoid the energetic costs. Is just slow down, and that probably gives you the stability, because you have longer to get the visual information you need. You can find the good footsteps in time, and yeah, slowing down is something we do all the time. Also, even when we start thinking while walking, you'll slow down. So yeah, that's a big one. I don't know about individuals, but yeah, it would be interesting. Again, this probably could be easily adapted to aging people and things like that.
My name is Swami Gopal-Swami from Texas A&M. I'm working on autonomous vehicles. I found this presentation is fascinating. Thanks very much for that. So one of the questions that came to my mind is when you're walking, the gaze seems to be looking at two different types of things, right? Based on the angle. You did have a chart on the percentage of time that they may spend in one versus the other, depending on the terrain. But do you also have a sense for what kind of mental model they may have on based on the two different gazes? So one a more detailed terrain model mentally, and then one an environment model that could in turn perhaps drive their decision-making process.
Yeah, totally. I think that's a lovely question. It's not something we've got to in any detail, but I think that the longer the looks in the distance, you say yes, well, this is a good direction for me to head, and so that might sort of set your criterion for you don't want to deviate from that direction, so it might constrain you in that way. But yeah, I think there's a whole lot of really nice questions there, and definitely those looks are for different purposes. And yeah, initially we were trying to think of I wonder when you time those looks in the distance at a certain phase in the gate cycle, or we haven't looked at any of those things. That would be nice to do. Yep.
I don't know if you can. So I have a bit of a tangential question. I'm a student here at UT, and we use virtual reality for a lot of our experiments. Perceptual experiments.
One of the things that we have been working on is a somewhat different question, which is, so when during the gait cycle, you generate these complex motion patterns on the retina, and we think that that's probably regulating your posture. And so we've been looking at that particular thing because historically, again, in the vision field, people have taken these flow patterns on the retina and said, oh, you use that to guide where you're heading. And, so we were just testing that. No, we actually think it's much more local. And if you get a sort of a biased set of motion vectors, then you're falling or something like that. And so I think there are lots of really interesting things to do, and we haven't actually got around to even planning them at this point. But yeah, I think it's
then Mitch.
Hey, I'm up here.
Hi.
I'm from him. I really enjoyed your talk, and I think I took your class when I was a grad student here. But then one of the things that you mentioned, the 5-step planning, relates, I think, to we had to do a similar experiment where we were walking on level ground, and we were not interested in gaze, but we level ground transitions to stairs, and how far in advance people alter their coordination and muscle activity and things like that. And we actually showed if you're counting steps, so 2 strides of each side, each leg, that even as far away as that, so 4 steps away, people like downregulate muscle activity or upregulate muscle activity, depending on which foot is going to be the first that touches the stairs.
Perfect.
So kind of really cool stuff, but not at all interested in gaze, but it seems so relevant.
Consistent,
Yeah.
About this.
And then I guess my question would be that how do you square the concept of like central pattern generators, right? Where people think that most of the circuitry for locomotion is like within the spinal cord versus in the brain, the brain directly driving locomotion. So some people sort of think that people are unstable when the brain kind of gets in the way, right? When you have to make a conscious decision as opposed to just being sort of an autopilot on flat ground. Have you studied anything to do with how the brain activity changes with the different severities of the terrain?
No, that requires somebody with skills
brain,
in physiology. But I think the trouble is it's really you sort of limited, like none of the animal work. You just can't record them when they're walking, and so it's just human work and the precision of the spatial precision is limited too. So I think people don't know as much about this as they should, but I think that I don't think the cortical control is, I think everything's cortically controlled. And so, you've got the loop through the cerebellum, and so the signal that's coming down from motor cortex is already, it's had a lot of fine tuning from the cerebellum and things like that. So I think, I don't see cortical control as a problem. Everything has to be cortically controlled, it's just like, I think, but I mean, interestingly, there are other things, this is a little bit of a tangent, but the vestibulo-ocular reflex, which stabilizes, the gain goes up when you're walking. So somehow or other, the spinal cord is saying, hey, you're walking, better amp up that gain so you get a good visual signal, right? So it seems to me that they have to be able to talk to each other seamlessly.
Thank you.
One final question, and then we'll break.
This is great. This is the kind of data set that is always going to lead to 1,000 more questions with everything you do. And so it could easily devolve into, did you consider X, Y, or Z? But I'm going to ask you about two anyway. One is, there was the creek, which seemed to kind of predefine a general path that they would take. And I'm wondering if it was an open rock field, if you had the idea that maybe people would have looked up more, even in a rocky area, because of more freedom on what path they could take, and if there was a restriction there. That was number one. And the second one is, I know that when I climb on rocks like that, I spend a lot of time trying to guess whether that rock is going to be stable or sink or not. And I'm wondering if there was any way that you were able to figure out to possibly include that in the prediction model.
The first one is, I think people just, what's the quickest way for me to get where I'm going? And so as long as you have a goal, we all want to take a straight path. That's our first, and I think that's a real constraint on what you do. In terms of the stability, I kind of think we're a little bit kind of gazelle-like, and so that might be something where you can leave it to, either learn, maybe some of the reflex circuits to sort of, so you step on this, little wobbles a little bit, and so you quickly change your weight. So there's a huge number of interesting things about locomotion that we're just not even touching on here. And I'm actually, I used to think, locomotion, that's really boring, And but when John came and I said, maybe it's interesting, but I'm not actually that much of an expert on locomotion. I'm just, it's a huge field, and so I'm really just focusing on the visual control, and in this case.
Well, thanks so much, Mary. This is a fascinating talk, and I'm sure I'm going to ask on behalf of all of the roboticists who are dying to ask you. We would love to get hold of some of this data to actually teach our robots, so we should chat more.
Oh, totally. I think that would be fabulous. Yeah. No, I'm really excited at the possibility of making these data sets available. So.
Yes, and I'm sure there'll be lots more questions. Let's take it over the coffee break. We're going to break for a coffee break. Let's thank Mary.
Thank you.